Hello and welcome to the 36th webinar in 12D's Industry Solutions webinar series. My name is Lisa Stewart and I'm the Marketing and Communications Coordinator here at 12D Solutions. Our Industry Solutions webinars are designed to provide insights into overcoming challenges in an evolving industry in more effective and efficient ways. We'll keep running these webinars regularly and recording them for posting on our YouTube channel with links through our website. Our first 35 webinars from this Industry Solutions series, as well as the 40 webinars from our training series, are available online if you missed those. During this live presentation, you'll be able to type your questions along the way, as shown on the screen, and we'll answer as many as possible throughout the webinar. At the end, I'll also read out some of your questions to the presenter for his insights if there's time. Today's webinar, Dynamic Culvert Designer, will be presented by Jeff Thompson, who has been a Senior Water Resources Engineer at 12D Solutions for around 10 years. Jeff has a total of 35 years of involvement in civil engineering software and was the co-founder of XP Software, which he directed for 25 years. The Dynamic Culvert application is a component of 12D Model's Dynamic Drainage module that allows the user to design and analyze single or multi-cell culverts of multiple configurations and shapes. By using the same unsteady flow analysis engine as the Dynamic Drainage module, it is capable of handling adverse grades, any shape including box, pipe, ellipse, egg, arch, horseshoe, and even user-defined, any inlet configuration, flared, tapered, bevelled, etc., roadway weir overtopping using simple and compound weirs and FHWA HDS5 methodology, and tailwater conditions including free, fixed, and user-defined open channels. It also includes comprehensive reporting. Over to you, Jeff.
Yeah, thank you, Lisa. Well done. I didn't know we did all that. This webinar we're going to focus on the hydraulic analysis and design of the culverts, and it'll use a macro written in the 12D programming language, and it's going to use the 12D Dynamic Drainage Analysis engine, the same one we use in our 1D unsteady flow modelling. Now we're going to be looking only at the hydraulic design, not on the set out construction or no 3D visualisation, none of the eye candy you'd probably be used to from if you've been to any Owen or any of Rob's webinars. We're just targeting it purely on the hydraulic analysis. So the macro is written around the minimum data requirements needed for hydraulic analysis. So there's basically three components. So we've got a culvert, so we can handle up to 5 unique culverts, each with multiple barrels, and if you've got box culverts including link slabs. Then our second component that we need is some weir data, so what happens when the low point in the road is exceeded and the flow starts to overtop, and then a boundary condition at the downstream end, so a tailwater condition. Now, hydraulically, culverts are a bit more complex than it would appear at first glance. They're subject to both inlet and outlet control, and they'll generally switch from one regime to the other as the flow changes, as the flow increases. In fact, there's US Geological Survey estimated there are 18 different regimes that flow can take through a culvert. So fairly complex networks. So we have two types of controls in culverts. So there's outlet control. Outlet control is pretty well understood. The flow is controlled by the physical characteristics of the culvert, so the length, the grade, the cross-sectional area, the roughness, any energy losses, and the headwater and tailwater. For most culverts, flow would be subcritical. Okay, about 200 years ago, Navier-Stokes developed some equations for fluid modelling, and the equations are a bit too big to fit on my screen. So, but the equations are used for any viscous fluid, so they could be used for modelling air, weather patterns, flow over the wings, even down to pipe flows, but very, very complex. So again, about 200 years ago, Saint-Venant took the Navier-Stokes equations, tossed out all the bits that didn't matter, or that he thought didn't matter, and gave us the Saint-Venant equations, which is still considered, even to this day, state of the art. So this was all done about 200 years ago. This is a 1D form of the equation that we use in our 1D dynamic drainage analysis, and a modified version of this is used for 2D flow in the 2D module. So although the maths has been around for a long time, for almost 200 years, it hasn't been widely adopted because there's no direct solution. So until the use of computers became widespread, it wasn't really practical, and it was generally simplified. So most of you would be used to the kinematic wave approximation, where we've just got the, that can be solved on a calculator or on a slide rule if you like. Stick that in your spreadsheet and the world's a happy place. But unfortunately it doesn't really apply, and we can't model siphons, we can't model adverse grades, we can't model switches from supercritical to subcritical flow and so on. So we really do need these extra terms. So the second part of culvert design is inlet control, and it's not particularly well defined. The concept is fine. Flow is generally supercritical, and the culvert characteristics don't play any role in the calculations. It's only influenced by the headwater and the inlet configuration, but quantifying it's another matter. So we know there are three main components. There's the face section, the bend section, and throat section of a culvert. And at various times, the face controls the flow, the bend might control the flow, or the throat might control the flow. So we wind up with an overall performance curve. But as I mentioned, quantifying them's quite difficult. In the late 1940s, the US Bureau of Public Roads put forward a proposal for a 65,000 kilometre national system of interstate highways. But they saw the $100-odd billion price tag and croaked, and didn't happen. Now, fortunately, the Cold War came along, and in 1956, the Department of Defence came on board, and they renamed their proposal the National System of Interstate and Defence Highways, and the FHWA was born. Now, they didn't want their troop transports and their temporary runway network to become unpassable due to hydraulic failures, and so with an open checkbook, they took to researching culvert flow and developed physical models, some of them full scale, for 60-odd inlet configurations, and came up with empirical nomographs and later on equations, and published design procedure for highway cross drainage, which is what we've used here, the FHWA HDS5, hydraulic design of highway culverts. So, as I said, normally a culvert will change from inlet to outlet control as the discharge increases, and generally from supercritical to subcritical flow, so we'll get a hydraulic jump in the culvert at some stage. But by using those momentum equations, continuity equations in the Somfenant solution, we're able to model fairly complex culverts. So we can model broken back culverts and bends through culverts, and culverts that transition from mild to steep slopes and so on. Now again, because they had a pretty much an open checkbook, they also considered that roadway overtopping was quite an important part of the modelling of the culverts. So they looked at practical aspects of roadway weir flow for both paved and gravel roads, and came up with weir discharge coefficients that are more relevant to the road's physical characteristics. So they're looking at the headwater depth, the tailwater depth, the width of the road where it overtops, and then you can come up with a coefficient of discharge for your weir. So, and this is one of the methods that we now have available in this macro. So I'm going to switch to a live demo of the software now, I hope. Yep, good. Okay, so all I've done here is just opened up a new project. If I can get my mouse work. So there's no models in it, it's just an empty project. And I'll go to design, drainage sewer. This is version 12, by the way, people. Dynamic culvert. Okay, and we'll open it up. Okay, so we have a home screen that allows us to turn on and off culverts and allows us to design for different situations. So we can design for water surface level, we can design for culvert size, we can design for culvert flow, and we can create a rating curve of information. Okay. We can also have preferred pipes that we use in our design, so we can load the defaults. If you're familiar with using the 12D drainage module, we can also open up a preferred pipes file that you might have created. Now, but we have a whole bunch of default values built in for pipes, for boxes, for horizontal ellipses, vertical ellipses, arches, and pipe arches. Okay, probably the most important component here is the culvert data that we're going to add. So, as I said, we can have 5 culverts. We can switch them on and off using this use culvert flag. So if I turn this one on, I'm going to use culvert number 1. The types of culverts I can have are the pipe, box, ellipse, arch, pipe arch, custom, which is a user-defined shape, and then some fairly esoteric ones, rectangular, triangular bottom, and basket handles and eggs and horseshoes and Gothic and catenary and yeah, a whole bunch of things that you probably never use. But anyway, for now, let's just go with the pipe. So as we change the culvert type, our shapes that are available will change. So for a pipe, we can have either a circular concrete pipe, a corrugated metal pipe, a circular pipe, a circular with a tapered inlet, elliptical, so on. You'll see if I was to change that to a box culvert, we'd have different configurations, different types of wing wall flares and so on. So let's go back to the pipe culvert. So we've got a pipe culvert. We're just going to make it circular concrete. We can now set wing wall configurations for that. So let's just go with a square edge wing wall. Now we can set our upstream invert. Let's go, I don't know, 100. I just put in a slope and a length, say 10 meters. If I just clear that, it'll calculate what the slope is. Okay, number of barrels 1, a Manning's end, let's go 0.013, say. Diameter, if I just make it a meter, make it simple. We can put in entrance and exit losses, other losses, so bend losses and so on. We can also have sediment in the culvert, so sediment will fill the culvert from the bottom up, or we can choke the culvert. So the choke reduces the area of the culvert that's used for the inlet control calculations. And then we need to put in a road low point. Let's go 106, make it 6 meters deep. Okay, and we've got a culvert. Okay, so I said there's 3 components. First one, the culvert. Second one's weir data. So the weirs that we've got are transverse, side flow, V-notch weir, trapezoidal weir, and then these last 2, roadway overtopping and roadway overtopping HDS5, are the ones that were developed by the FHWA as part of that interstate highways project. So what they will do is you take your road profile, you put it in here, it creates a whole bunch of vertical slices along the profile of the road and generates weir flow over each of those, so using different coefficients of discharge for every metre of length along the road. So anyway, to keep it simple, let's just go with a transverse. I'll make it, I don't know, 2 meters deep, 10 meters wide. Discharge coefficient, let's go 1.7. So that's your weir data. The other thing we need is tailwater data. So I'll go, so tailwater conditions, we can have a fixed tailwater, we can have use the normal, excuse me, the normal depth in the culvert or the critical depth in the culvert or the minimum of normal and critical. We can have a rating curve, which would be similar to a fixed tailwater, but it changes depending on the inflow. Or we can have a downstream channel, so we can define a cross-section of a channel downstream of the culvert, and we can use the the normal depth or the free depth in the culvert, in the channel. So let's go with, I'll just go with minimum of critical and normal. It's pretty simple. Now if we go back to our main window, okay, the analysis engine by default takes an input of the flow and it returns the water surface elevation. So if we're going to solve for water surface level, that's the sort of the normal single run that this would do. If we want to solve for, say, culvert size or culvert flow, it's an iterative solution. So we have to come in, say enter a flow. It'll eventually return a water surface level equal to whatever value you've put in there. And it'll use a method of successive approximations to iterate on a solution. So for the moment, let's just pick the water surface level. This is going to be the quickest one. And we'll do a design flow of 1 cubic metre per second. Solve that. It'll run the 1D dynamic drainage analysis engine. It's given us a flow, and we've got so we can add a, let's have another flow of, let's do a design. Go for break. It's designed for culvert flow. What happens if we get up to, say, 104 metres? What sort of flow could we put through the culvert? So now it's going to do an iterative solution. It's going to calculate a flow, and again, and probably again, and again. Hopefully eventually we'll get to a solution. If I'd thought to open the output window down the bottom there, you could see what flows it was coming up with as it was solving. Oh. Okay, so at an elevation of 104 metres, we can get 14.8 cumex through the pipe. Okay, so the other one we can solve for is culvert size. It'll do it, but it'll be far more time consuming than culvert flow. And because we're just doing a single culvert, personally I think it's better for you to have some input into it, because you have more of a feeling, I think, as the designer as to what's suitable. In a large network, I think it's better if the computer does it, but for a single pipe, yeah, I found that it's often a lot quicker for you to do it by hand. Anyway, that's the end of our simple design. So if I finish that and I open it up again, you'll see it'll restore back to where it was when we closed it down. So it'll keep our last solved culvert there. Okay, now this is running as a independent application. You basically don't have to know anything about 12D at this stage. All you have to be able to do is find the icon, click open, type in the name of the, click new, type in the name of the new project you want to create, and that's it. And then find this on the menu. Now, if you wanted to do it, now if we want to integrate it with the drainage string that's in 12D, we can go to File, Data Input, 12D, 12DA Library. So these are all the samples that are shipped with 12D. So if we go to Drainage, and we can click on Culvert Dynamic, and let's give that a model name. Let's just call it Culvert, and import it. Now just go to this view and turn on the culvert. Okay, and that's the culvert that we've just imported. So there's our culvert. Okay, now let's go to add a second culvert to it. So we'll go to culvert 2 and turn it on. And now we'll pick the culvert from our drainage string. So this could be a whole network, so not just a single pipe. It could be, multiple pipes in your network, but you just pick the pipe you're interested in. Or we could pick it from the string or the pit or the pipe in the model. Anyway, that will now load up our culvert in here. If we go back to our original one, there'll be, okay, sorry. The road low point got changed. Let's just make, okay, you can see we've now got our 2 culverts there. So let's turn off our first one. We'll just go to the second one for the moment. And let's solve that. So let's just solve it for water surface level. We'll put in a QMAC again and solve that. Okay, I think I can get away with a bit less. How about we go to that culvert? Let's make it a 0.5. I know there's unstandard sizes. I'm just picking numbers out of the top of my head. Solve it again. So you can go through and play around with this. Then at the end, we can go back to our culvert, then go save it to the D&E. It'll put it back into our drainage string, and there's our resized and redesigned pipe. So that's pretty much it. If I just open up one that's got a few more, rather than create all these options, I've got one that's got a few things set up. Drainage sewer. So here we've got an example that actually has multiple flows, so we can solve for all flows. It has 3 culverts, so it has a circular concrete pipe culvert. It has another circular pipe culvert, but running at an adverse grade. And it also has a horizontal ellipse. So 3 different culvert types. Our weir data, in this case, we're using the FHWA procedure using the roadway overtopping. So what it's going to do, this is a profile of the road. What it's going to do is create some vertical slices down here, calculate a new weir discharge coefficient for each of those weirs, and then calculate a composite flow across the roadway. So it can also be, we went through those, transverse, side flow, V-notch and so on. Okay. The tailwater data, in this example, we're using rating curve. Okay. Although it could be a channel, some channel downstream. So we can have different left and right bank roughnesses, different main channel roughness. And then we can solve for the normal depth in this downstream channel, and we'll use that as our tailwater condition for our culvert. Rating curve. Now, if none of those culvert shapes work for you, so, if none of these work, we can also go to custom shapes, in which case we can define our own shape, where we enter the height of the conduit and the width. So it's a closed conduit shape. It'll then divide this up into, I think it's 50 slices, and then it'll solve this as your new hydraulic element. Okay, the other thing we didn't get into was results. Okay, so we've run a number of flows here. All what you see is the design flow, which is the flow that we entered and we wanted to solve for. And because it's an iterative solution, the actual flow that it comes up with might not be exactly the same as the design flow. It'll iterate till within 5 millimetres, I think. Once the two levels are within 5 millimetres, it says, okay, we've got a flow. This is converged, and this was the flow that it found it first converged at. We could run it down to a millimetre, we could run it down to a fraction of a millimetre. All it does is increase your run times exponentially, but doesn't really give you any better result. Actually, I think it might be a millimetre, not 5 millimetres. Okay, so the real results we get out of this now is if I click on this will give us the results for the 0.2 cubic flow for culvert 1, culvert 2, culvert 4, so only culvert 1 has got any flow through it. Let's go to one where we're starting to get some. So we're still below ground level. Okay, so when we get to 75 cubic metres per second, we've got 2.4 cubics going through the first culvert, 11 through the second, 2.5 through the fourth, and 58 over the weir. So then the parameters that we get fed from that, from the result, so the Q full, which is Manning's equation, the percentage full, which is the maximum flow over Q full, the depth in the midpoint of the culvert, the depth to diameter ratio or depth to height ratio, the velocity in the center of the barrel, the flow area at the center of the barrel, wetted perimeter, top width, Froude number, critical depth, critical slope, velocity head, specific energy, normal depth, flow type, so the flow type curve, whether it's under inlet or outlet control, the H-shells upstream and downstream, the depths upstream and downstream, velocities upstream and downstream, and so on. So it'll give us that for each conduit. So if we go back to our first one, so if we click on one of these, we'll see that show us what the profile looks like for each of these flows that we've selected. Okay. And the only thing that I haven't shown you is notes. So notes just allows you to add some notes relevant to this particular culvert. So yeah, you'll know why you designed it the way you designed it. So that's about 30 minutes, and I think that's probably pretty much covers it. Back to Lisa.
Thanks, Jeff. We've had a few questions through, so I'll read out a couple here. Adrian has asked, when we have 3 flows and 5 different culverts specified, for example, does it solve all 3 flows for the 5 culverts?
When we have 3 flows, yes, it does. Yes, the answer is yes. It's the roadway crossing from the upstream face to the downstream face of the road now comprises 3 culverts. So it's like a compound system of 3 culverts. Yeah, so all 3 of those culverts are basically solved simultaneously, and the flows through each of the culverts are what you would get when it iterates on the head and eventually gets a balanced network. So yeah, the answer is yes. Yeah.
Sure. And is upstream velocity 0?
Oh, okay. A culvert usually assumes that we're in a like a retarding basin, right? So it's the water level 0 until it enters the culvert, and then the flow starts to accelerate. If you are in the situation where you're going to have momentum transfer from upstream to downstream, you'd probably model the culvert as part of a dynamic drainage string. So you've got momentum transfer from the downstream conduit to into the culvert. So you might model it with a channel coming in from upstream, or with another pipe coming into a larger pit. Yeah.
Great. And Stephen Melbourne has asked, is there any documentation on this macro?
Oh yeah, there's Notice down the bottom is a little help window. If we click on that, we'll get the standard 12D, the help window, which will pop up. So it gives you all the help on the data. There's some sample values for losses and so on. Yeah, anyway, there's sort of reasonably comprehensive help. Okay.
Okay, and Kim in Sydney has said, can the culverts be set up to run in series?
As part of the 1D, as part of the dynamic drainage module, yes. Everything that we're doing in this culvert macro is available from within the 1D drainage model. So you could have culvert to culvert to culvert if you wanted. Yep. But this particular one, the culverts are in parallel, or yep.
Thanks, and I'll just take one more question live. Adam in Brisbane would like to know, what sort of reporting options are there that I could provide to a client?
Okay, yeah, we didn't cover that. Okay, if we click on the right button here, it will, okay, it's done, create a file. I'll just browse to it. No, and again, it's opened it up on the wrong spot. So it creates an HTML report that has all the culvert data, weir data, the way you analyse it, any of the graphs that you might have, all of the results for each flow that you analysed. And then at the bottom, a rating curve graph. So, which I should mention, the weir top, the reason we have a weir top shown, you think a weir should be of infinite depth, but we can actually allow a weir to go under pressure. So if the flow is to exceed the weir top, then it would treat it as an orifice and it would channel the flow through an orifice. So that's the reason we graph a weir top. So.
Thanks, Jeff. And thanks to the audience for your great questions. Sorry to anyone we didn't answer live. We'll get back to you individually by email. Our next two Industry Solutions webinars will be work sharing among multiple offices on the 20th of April, and then a great What's Coming series early in May. If you register for those now, if you haven't already, and keep an eye on our emails and social media channels for more great upcoming topics in this and our training series. And don't forget, as shown on the screen, our technical forum is on in Brisbane this July with the Associated Innovation Awards. The closing date for those is the 30th of April, so enter now for a shot and an amazing prize. If you need to contact us in the meantime, we'll pop some details on the screen for you. That concludes our presentation for today. Thank you for attending, and we hope to see you at future webinars.